So thank you everybody for coming to our next seminar. The speaker today is Hanchen, and he's going to be talking about the scalable HLS. So this is a work that I'm very interested to know more details. I know it's been a collaboration between his work in Illinois with Silence. And thank you for coming for the talk. Now the mic is yours.
Thanks. Okay, then I will start. Hello, everyone. Welcome, and my name is Hanchen Ye, and today I will talk about scalable HLS synthesis through MLIR. So this is a collaboration work from Illinois, Georgia Tech, SAL, and Xilinx. And so today I will first talk about the motivations, and then I will give you some background about the framework, the compiler infrastructure we are using. It is called MLIR. And then I will go through the framework and the optimizations and the design space exploration of ScaleHLS. Then I will provide some evaluation results before we conclude this presentation. So first, in case some audience are not familiar with HLS synthesis. So basically, HLS synthesis, or we call it HLS, is a compilation flow to translate high-level descriptions of programs into a hardware RTL design. And the high-level description can be written in any high-level languages. A typical input is C or C++. And the output, typically, it will be Verilog or VHDL. And in the compilation pipeline of HLS, there's typically 3 stages. The first is scheduling. Scheduling here means originally in the C or C++, we are describe the program in a serial manner. So basically you have a set of operations and they will be executed on the CPU one by one in a serial manner. But when we execute this problem or map this program onto a hardware or onto a RTL design, we desire the operations that can be parallelized to be executed in parallel. So the scheduling is just try to find the dependencies between the operations and make the parallel and make the program into a parallel execution model. And then the allocation stage is to allocate registers to the program. And finally, binding is to you have memory and computation resources on your hardware, and you have many operations in the IR. Then you need to bind the operations in your software program into the hardware components. And then we will have RTL design, which can be mapped to FPGA, ASIC, anything you want to target. And so studies have shown that HLS synthesis are providing many advantages. For example, the first one is it can significantly reduce the complexity of the design. It has shown that the code density can be reduced by 7x to 8x by moving from RTL to C or C++. And secondly, it can improve the design productivity. It can help the designer to get to work done faster and reduce the time to market. And finally, HLS can also help designers to quickly identify the performance area trade-offs, because you can implement different design choices very quickly and avoid those premature optimizations. Although HLS are providing all of these advantages, designing HLS accelerator is still challenging. So here is a very interesting experiment. Students are requested to accelerate a certain model using CPU, GPU, and FPGA. And when targeting FPGA, they are asked to use HLS synthesis to design the accelerator. And this figure shows the percentage of student submissions in each performance range. Here, the performance are normalized with respect to 75% of expert design performance. So you can observe almost all of the FPGA summations fall into the range of from 0 to 0.2. That means actually Halo synthesis is somehow rely on the designers to write good code to achieve a high design quality. And there is a large margin between expert and newcomers. So we can say Halo synthesis is more friendly to experts. And secondly, because you can quickly implement different optimizations and different combinations of these applicable optimizations on a Halo synthesis design. That means these optimizations can form a very large design space, especially for those large-scale Halo synthesis designs. And this actually makes exhaustive exploration infeasible. And finally, some recent studies have also shown that there's some complicated correlations between different design factors or optimizations. And it's difficult for humans to discover those complicated correlations and make the right design choice. And all of these are some challenges of designing HLS accelerators. And ScaleHLS is trying to tackle these challenges in a step. So before we talk about the detail of ScaleHLS, let's first look back and ask a question: how do we do Halo synthesis designs? I believe different people will have different answers, but here I will try to abstract a typical, procedure of how people do HLS designs. This is a very short example. It's a C snippet. Actually, it's a matrix multiplication. And when we try to map such a C program onto hardware with Halo synthesis, one thing we need to do is to use directives to optimize the C code, because almost all Halo synthesis tools use program directives to tune the hardware generation and improve the design quality. For example, here, we inserted an HLS pipeline pragma or directive to the innermost loop level. This will pipeline the loop body of this K loop and make all the statements or operations in the loop body work in a pipeline manner, which can improve the latency and throughput of this, this loop nest. And apart from the pipeline directive, we also have several other directives. For example, the loop unrolling, and for functions, we have function pipelining, function inlining, and we can also partition arrays. And if you don't familiar with these directives, I will introduce them in a second. And after we optimize the C program with the directives, we can pass them to the high-level synthesis tools. For example, Vivaldo Halo Synthesis and Xilinx Vitis Halo Synthesis to generate the RTL code. But typically, when we do a real Halo Synthesis design, in most cases, just applying those directive optimizations is not enough. Actually, we highly rely on loop optimizations to further improve the performance and the design quality. For example, here, in this example, we actually interchanged the K loop from the innermost loop level to the outermost. This is because the loop interchanging can help you to change the dependency instance and help to improve the quality of the pipeline. And meanwhile, originally there's a statement in between the J loop and K loop, but here we apply a loop perfectization to move this statement into the innermost loop body to make actually the K loop and I loop flattened into the pipeline loop to further improve the pipeline quality. So actually through these loop optimizations and together with the loop pipelining we applied, we can significantly improve the performance of the generated hardware. And apart from the loop interchanging and perfectization, we also have all of the other traditional, loop transformation techniques. For example, loop tiling, loop scaling, and extra to do the loop optimizations. And now we already have two optimizations, it's loop and directive. But in a real high-level design, we typically are not dealing with just one loops. We will have a set of loops, and we have dependencies between each other. And such a program can form a thing similar to a computation graph. Like here, in this computation graph, we have 4 nodes, an input node, a convolution, a sampling, and a matrix multiplication. And this is, I would say, a higher level than the loop. And at this level, we also have multiple optimizations can be applied. For example, assume we can fuse the convolution node and the sampling node into one IP, into one node, and map it to optimized hardware IP. Then we will have 3 nodes in the graph. And then maybe we want to make this 3 nodes work in parallel. Then we can apply something called task level pipeline to make this 3 nodes work in parallel in a pipeline manner. And for these high-level optimizations, we can abstract them as graph optimizations. So you can observe, for now, we have 3 levels of optimizations: graph, loop, and directives. All of these optimizations are desired during the procedure of high-level design. And now, if we look back to the original question, how do we do high-level designs? Basically, the answer is manual code rewriting. We need to rewrite the code to fuse the node and do the IP integration and apply the task level pipeline, and basically ×3. So such an approach has several problems. First, it is low productive and error prone, especially when you are dealing with not tens of code, but thousands of lines of code. Then such a manual code rewriting is very low productive. And meanwhile, because you cannot easily try different design choices, so it's hard to enable an automated design space exploration. And finally, this kind of procedure is not scalable for large HLS designs. So then, ScaleHLS is trying to solve these difficulties. We observed that these high-level synthesis optimizations are desired to be applied at different abstraction level. For example, the graph abstraction level is higher than loop and higher than directive. And these problems can be solved well at different abstraction levels. That means we are desired to solve these problems at the correct level and automate all of these optimizations to make a design space exploration possible. And such a hierarchical optimization procedure perfectly fit into the scope of MLIR. So MLIR stands for multi-level intermediate representation, and I will briefly introduce MLIR in a second. So basically, it's a compiler infrastructure that can allow us to quickly implement such a multi-level representation and optimization problem. So the approaches of ScaleHLS is, as a first step, we need to represent the high-level design at multiple levels of abstraction. And then we need to make all of these optimizations shown here automated and parameterized. And on top of the multi-level optimization interface, we can enable an automated design space exploration. And finally, we hope to have an end-to-end high-level synthesis and optimization flow. All right, then I will briefly introduce MLIR. So now MLIR is a part of LVM, but actually MLIR, you can consider it as a meta IR, which where LVM is a subset of MLIR. Because in MLIR, you can easily define operations at different abstraction level and do transform and conversion and analysis on top of the operations you are defining. And LVM becomes the lowest level of representation in the MLIR world. And meanwhile, the MLIR framework is modular, extensible, and general to many domains. So now we are using MLIR to do Hello synthesis, and many other people are trying to use MLIR to solve many other different problems. And if you are, interested in more details of MLIR, you can look into this presentation by Chris Lerner, and also the CGO keynote talk slides. All right, then let's talk about the framework of ScaleHLS. As we previously mentioned, the first step is to represent the high-level synthesis designs in MLIR. So here in ScaleHLS, we have 3 levels of IR. And for the graph level IR, we're using third-party dialects called Onyx and A10 to represent the graph level IR. And here is a very simple example of a jam operation in Onyx. You can observe at the graph level, the operation are taking this tensor values as operand and generate other tensor results, and it's pretty high level. And then this kind of graph level IR can be lowered to the loop level IR. And here in ScaleHLS, we use the affine and SCF dialect to represent the loop level IR. Basically, the affine dialect is trying to represent the loop structure explicitly in the IR. Like here we shows. We have a very structured IR here using affine 4 to represent the 4 loops. And you can observe actually here the structure is very similar to what you will write in a C code. It explicitly represents the I loop, J loop, and K loop rather than using the branch. There's also some other operations such as affine load operation, affine store operation to represent the memory access behavior in the IR. And the benefit of the affine dialect is we can easily use the polyhedral compilation techniques on top of such a loop level IR to facilitate the transformation and analysis for the loops. And MLIR also provide many useful and powerful transformation analysis libraries for the affine and SF dialect. Then we want to enable the directives representation in ScaleHLS. So we introduce a dialect called HLCPP to represent those HL-specific directive structures in MLIR. For example, here, we have 3 levels of loops. And for each level of loop, we attach a HLCPP attribute called loop directive to it. And you can observe for the innermost loop level, we have a pipeline directive applied on it. And and for the outer 2 loops, a plan is set to 0, which means it is off. So we use such a HLCPP dialect to represent those loop directives, array directives, and function directives as well. So these 3 levels of IR forms the representation of ScaleHLS. And on top of these 3 levels of IR, we can easily apply those optimizations we mentioned before. So as the next step, we will introduce the optimization of ScaleHLS. So we develop a set of optimization paths for each level of IR, including graph, loop, and directive. And here we intend to solve the optimization problems at the correct abstraction level. And meanwhile, apart from the optimization process, we also provide a quality of result estimator to take the directive level IR in and analyze the IR and estimate the latency and resource utilization of the design. Basically, it can help the compiler to better understanding, the quality of the design to help to apply some other optimizations and the design space exploration. So this is the optimization and the analysis process we are providing in ScaleHLS. And on top of the optimization of ScaleHLS, naturally, we hope to build the design space exploration. So here, we first parameterize all of the optimization process and package them into we call transform and analysis library. And this becomes a perfect playground for design space exploration. And on top of the library, we design an automated DSE engine, which can find the Pareto frontier of the throughput area trade-off design space. And finally, we introduce an HLC frontend to parse C programs into the MLIR framework. And in the end, we provide an HLC or C++ emitter to emit the directive level IR into a synthesizable C or C++ code, which can be passed to the downstream tools like Vivado HLS to generate RTL code. And you can observe here, actually, we can also lower the directive level IR into LVM, which can be passed to those LVM compatible high-level synthesis tools. All right, so this is the overview of the ScaleHLS framework. Then I will introduce the optimizations happening in ScaleHLS. First, let's talk about the graph level optimizations. We are providing two graph level optimization processes here. We call it legalized data flow and split function. And this is a running example. It is a computation graph with 5 procedures. And at the graph level, as we mentioned, we want to apply a coarse-grained pipelining to the computation graph to make the procedures in this graph work concurrently and work in a pipeline manner. And such a coarse-grained pipelining is also called data flow in some high-level synthesis tools. And typically, the downstream high-level synthesis tools will have some requirement for coarse-grained pipelining. For example, typically, they will not allow a bypass path between different pipeline stages to avoid data pollution. So here, conservatively, we can split the original computation graph into 3 pipeline stages to avoid the bypass paths. So you can observe the procedure 0 is stage 0, and procedure 1, 2, and 3 are split into 1 pipeline stage, is stage 1, and finally the last procedure is stage 2. So in this way, we have a 3-stage coarse-grained pipeline. And if we assume the latency of each procedure is 1T, then the interval of this coarse-grained pipeline is determined by the latency of stage 1, so it's 3T. And so here, the legalized data flow paths will identify those bypass paths and provide a legal data flow partition, like here. And then the split function path will split the procedures that are partitioned into the same pipeline stage to a new subfunction. So you can observe after the split function, these 3 procedure will appear in a subfunction called stage 1, and there will be a function call in the top function to call the subfunction of stage 1. But actually, we can do this more aggressively. Basically, we can insert some copy nodes or buffers to the bypass path to enable a more fine-grained pipelining. Like here, we have a 5-stage coarse-grained pipeline. How can we do this? We provide an insert copy parameter for the legalized data flow path. And if we turn on the insert copy option, it will automatically insert those copy nodes and buffers to the bypass path to enable the coarse-grained pipeline. And in this case, we can observe actually we can achieve a much fine-grained pipeline, achieve a lower interval, because now the longest stage has a latency of 1T. So the overall interval is 1T. Every 1T, we can pass in a new frame of data. And on top of this graph, we observe that actually we have a design space here at the graph level, because we can merge the adjacent pipeline stages into one to trade off between the throughput and the area. For example, here, we merge the adjacent pipeline stages into one. Then we have a 3-stage pipeline, and we can save some memory resources, such as the buffer here. And meanwhile, because the interval is increased, so you have more opportunity to do the resource sharing. So the computation resource will also be reduced. So in this way, we can trade off between the throughput and the resources we utilize. And here, we use a minimum granularity option for the split function path to tune the granularity of the pipelining here to trade off between the throughput and area. So this is the graph level optimization we are doing in ScaleHLS. And then, apart from graph level, we also have quite some loop level optimization directive and other simplification optimization passes provided in ScaleHLS. And here, the both phase ones are new passes developed by us, and the others are the MLIR built-in passes we leveraged in ScaleHLS. So here, I will not introduce each of them, the mechanism, each of them one by one. I will just give you an example to show how the loop directive and other optimization passes are optimizing the HLS designs. So here is C code. It's an SYRK kernel in the BLAS. And our target today is to optimize this C code with all of those optimization passes. So this C code will first be parsed into ScaleHLS through the HLC frontend. And then it will go through the loop and directive optimizations in MLIR. And finally, it is passed to the CLC++ emitter to emit the synthesizable C++ code, as shown here. So first, we have a loop perfectization optimization path to perfectize the nested loop. In this example, this statement is moved into the loop body. And then we have loop order permutation, which can automatically detect what is the loop order that can benefit the performance improvement and automatically apply the loop order permutation on the nested loop. For example, here, the K loop is permuted to the outermost. And meanwhile, we also have loop unrolling to unroll loops, like improve the parallelism of the computation to improve the performance. So here, the K loop actually is unrolled by a factor of 2. So the step here becomes 2, and actually the loop body is duplicated for 2 times. But after some other simplification passes, some operations is eliminated. And then we also have another pass called remove variable bound. You can observe here originally the J loop has a variable loop bound. The loop bound is like I. And for now, the MLIR infrastructure is focused on the constant loop bound and focus on the rectangular optimization loops for optimization. So here we provide such a remove variable bound path to try to remove those variable loop bounds. Like here, we will find the upper bound of the variable I. We find, oh, actually the upper bound is 32. Then we will replace the variable bound with a constant number, 32, and insert an if statement here to make sure the conditional execution of the original loop body. So in this way, we transform the original triangular nested loop to a rectangular iteration space, which can open the opportunity to do other optimizations and transformations in ML. And then for the directive optimizations, we have a loop pipelining path to automatically insert the pipeline directive to the HLS design. Here we insert a pipeline with an initial interval of 3 to the innermost loop level. And after that, we provide an array partition optimization path in ScaleHLS. This is because in this example, after the loop is unrolled, you can observe there will be 2 simultaneous array access operation in the loop body, which actually require enough on-chip memory bandwidth to achieve the expected parallelism. So here, the array A need to be partitioned with a factor of 2 to meet the requirement of the parallelism here. And the array partition path can identify this kind of memory access pattern and apply the suitable array partition strategy to the corresponding arrays. And here, the array A is partitioned with a cyclic partition fashion and with a factor of 2 on the second dimension, right? So in this way, you can access K, the index of K and K plus 1 simultaneously without conflict. And this is the directive optimizations. And we also provide optimizations like simplifying the if operations to remove those always true and always false if statements. And we also have store OP forward and simplify memory ref OPs to remove those redundant memory access operations to further improve the quality of the design. So here, actually, this code is already optimized by those optimization passes. All right. So after applying all of these passes, we have an optimized and synthesizable C code. And the next step will be design space exploration. So here, you can consider each parameter of optimization pass of an optimization path is a tunable knob in the design space exploration, or it is a dimension of the design space, which is tunable, right? So in this way, we can open a multi-dimensional design space to explore. Then how do we explore it? We provide a transform and analysis library to automate all of these optimizations and make them callable to enable the DSE. Then I will introduce the DSE algorithm we're adopting in the ScaleHLS framework. First, though, to better understand the design space we are facing, we did profiling to GMM kernel. And here is the profiling result, is the latency and the area space. And you can observe the points that are annotated as deep blue is the Pareto points of the design space. And our goal of the DSE is to find those Pareto points in the design space. Once we have such a Pareto frontier, given a resource constraint, we can find the optimal design point that can be provided. So if we map all of this design point back to the multidimensional design space we mentioned, it looks like this. So here, to visualize the multidimensional design space, we apply a principal component analysis to reduce the dimensions to 2. And you can observe, actually, the Pareto points are located at the corner of the design space, which means the variance of Pareto points is much smaller than the overall variance. So this is also true in the original multidimensional design space, actually. And on top of this observation, we developed a straightforward DSE algorithm. So as the first step, we will randomly sample the whole design space and evaluate each sampled design point with the quality result estimator. For example, here, we sampled a set of design points in the design space, and we evaluate the performance, the latency, and resource utilization of each design point, and find the Pareto frontier of this set of design points. And then we will evaluate the closest neighbor of a random selected design point in the current Pareto frontier. Here, we randomly selected one Pareto point, this one, and find the closest neighbor of this picked design point and evaluate it. The rationale of this step is based on the observation that variance of Pareto points are much smaller than overall variance. There's a high possibility that a neighbor of a Pareto point is another Pareto point. So we will evaluate this new point, and if it is a new Pareto point, then we'll add it to the Pareto frontier. And in the same time, if we found an old Pareto point is dominated by the new one, we'll remove it from the Pareto frontier. And in this way, we'll be able to keep updating the discovered Pareto frontier and make it better and better by repeating the step 2 and step 3. And finally, we will have an estimated Pareto frontier in the end. So because we cannot do an exhaustive search, so this is not real. This is not the real Pareto frontier. But as long as we have enough iteration number, it should be close to the real Pareto frontier and give a reasonable design space exploration result. So this is the current DSE algorithm in ScaleHLS. And I want to mention that on top of the transform and the analysis library provided by ScaleHLS, because all of the optimizations are automated and are ready to be called by the DSE engine. So you can easily extend the DSE engine to support other optimization algorithms to solve such a optimization problem. And then let's take a look at the result of the design space exploration. Basically, we pick 6 computation kernels from the Polybench benchmark, and we set the problem size to 4,096. And you can observe after the design space exploration, for most of benchmarks, we achieved hundreds of performance improvement compared to the baseline designs only optimized by Xilinx Vivado high-level synthesis. And here we also listed all the optimizations, all the optimization parameters picked by the DSE engine. So here, LP is loop perfectization, and RVB is remove variable bound. And here, the permutation map indicate the order of the loops after the permutation. And quite some improvement comes from the loop perfectization, remove variable bound, and loop permutation, because it can pipeline the loop, make all of the statements inside of the loop work concurrently. And meanwhile, the loop order permutation, as we mentioned, it can help to improve the initial interval that can be achieved by the loop pipeline. And meanwhile, this column shows that the tiling sizes of each loop level of the kernel. And here, the intra-loop, the intra-tile loops generated sunk into the innermost loop and fully enrolled. So actually, you can consider the factor here as the enroll factor, and the larger the factor here, the larger parallelism are applied to the corresponding loops.
So I have a quick question just to clarify. When the speed up, are you talking the total execution time of the benchmark? Are you talking about frequency, or what are you talking on the speed up?
It's the
compilation time, or what is this?
It's the latency. So basically,
the total latency and the frequency. Do you have the
under
frequency?
the same frequency, basically?
Yeah. Okay, same frequency.
Yeah. And here we also apply pipeline, and you can observe the II are also automatically selected by the DSE. Because basically, if you increase the II, you can do more resource sharing in the pipeline. And meanwhile, the performance or the latency will increase. Okay. And finally, suitable array partition strategy are applied to different arrays in the benchmark. So this is the DS result of the this 6 computation kernels. And to evaluate the scalability of the DSE engine, we also perform a scalability test. Basically, we scale the problem size from 32 to 4,096. And you can observe actually for most benchmarks, the speed up is quite stable. And for the GSU, MLV, and TRIM benchmark, on small kernel sizes, the speed up is like significantly smaller than the larger problem size. This is because actually for small kernel sizes, the design space is also small, which constrains the the DSE engine to fully utilize all the computational resources on the target platform. But overall, this figure is trying to show that the scalability of our DSE engine is quite well. All right, and then we also tested the ScaleHLS framework on some large and complicated benchmarks. We pick DNN models as example here. Basically, we pick 3 PyTorch DNN model and pass the PyTorch model into ScaleHLS and apply the graph loop and directive optimization passes to the DNN model, and finally generate synthesizable C++ code and pass to downstream HLS tools to generate the RTL. And here, the speed up is also over the baseline design, which is only optimized by the HLS. And you can observe for those very complicated, ResNet 18, there's like tens of loop nets in the model, and have very complicated dependencies between the DN layers. But we just use like 60 seconds to optimize the ResNet 18 model and achieve thousands of speed up. And if we compare with some widely accepted, DN acceleration framework such as TVM VTA, we actually achieve even better DSP efficiency than them. And to evaluate, the directive, the loop, the graph level optimizations have effect on those large benchmarks, we apply ablation study on top of these 3 benchmarks. If we look at the ResNet 18 benchmark, the D here represent the directive optimizations, and L represent loop optimization, while G is graph optimization. After we only apply the directive optimization, we achieve about 2.1x improvement. And then we add the loop level optimization, and the performance improvement significantly improved to 274 about. And then we apply the graph level optimizations, and the final speed up is like 3,800. And here, ScaleHLS allows the user to tune the optimization level for the loop optimization and the graph optimization. So basically, the number here, the larger it is, it actually indicates a stronger optimization. And so there's a similar trend for another 2 DN models. So this ablation study shows that the directive loop and graph optimization, the multi-level optimization methodology actually works pretty good on the large and complicated high-level synthesis designs. All right, and this is the experiment. So the conclusion, first we present a new framework called ScaleHLS, which is HLS compilation flow and can represent high-level synthesis design at multiple levels of representation and optimize HLS designs at different abstraction levels. And meanwhile, we package all of the optimization and analysis process to a transform and analysis library dedicated for high-level synthesis. And meanwhile, we provide an HLC frontend and a sensitizable CLC power emitter to enable the end-to-end compilation flow of ScaleHLS. And finally, on top of the optimization and representation, we provide an automated and extensible DSE engine to search for the optimal solutions. And experimental results actually demonstrate that we have a strong scalability to optimize large-scale and sophisticated HLS designs and achieve significant performance and productivity improvement. And also, ScaleHLS leaves several future directions to work on. The first is IP integration. So this is a very common graph level optimization we can apply on high-level synthesis designs. And the graph level representation of ScaleHLS actually enables the ability to integrate existing HLS IPs into the compilation flow. And meanwhile, we can also generate new IPs through launching the DSE engine of ScaleHLS. And the second one is DSE algorithms. We mentioned the parameterized interfaces provided by ScaleHLS actually is a perfect playground of DSE. It can enable a large opportunity, to investigate different optimization algorithms to solve the DSE problem. And the next one is machine learning based quality of result estimation. I didn't introduce the quality of result estimation in this presentation, but for now, we're using an analytical model based quality of results estimating algorithm to analyze the IR and generate the estimated latency and the resource utilization. But actually, we already observed some paper involving machine learning algorithm to better capture, the features of the program and generate more accurate quality result estimation. So this is also a very interesting direction that can be explored in the future. And finally, we're also looking at generating RTL code within MLIR. So currently, ScaleHLS are generating synthesizable C++ and rely on external backends for generating the RTL code. However, a direct RTL code generation can keep more information from the higher level IR, and potentially it can provide even better, optimization and quality of the RTL design. And a good news is we have some ongoing efforts. If you're familiar with that, it is called Circuit, which are trying to model the RTL level representation in MLIR and do the RTL optimizations on top of these RTL models in the MLIR. So in the future, we may be able to connect the ScaleHLS to those RTL dialects in MLIR to directly generate the RTL code inside of MLIR to further improve the quality. And that's it. Thanks.
So thank you. Very impressive. A lot of work. So I'm curious. So you already started to interface with, but maybe before I do some questions on my side, if there are some questions from students posted on the chat or the Q&A, and then we'll forward and maybe can promote you to speaker. But one of the questions that I was having is, have you started to interface with Circuit? And one of the things, like you were saying, that you generate C and then it goes to BTIS to generate the netlist. So what will be the advantage besides compilation time of going through the circuit flow?
Okay. Actually, we are also expecting to improve the the compilation time through the MLIR compilation. So if you look at the the backend part, for example, compiling the RTL design to netlist, and this part, Circuit already, let's see, I believe Circuit already achieved some advantages over the traditional compilation flows in terms of compilation time. And in terms of high-level synthesis, as I mentioned, we need to do the scheduling and allocation and binding for the high-level synthesis compilation. If we have a better internal immediate representation in the MLIR and do the traditional high-level synthesis compilation on top of the MLIR, I will also expect some compilation latency improvement in that part. So both of these two part is some future directions we can work on. And meanwhile, for now, because the Vivato high-level synthesis or other commercial tools takes arguably long time to do the compilation, which makes us hard to do the automated design space exploration. So we developed the quality of result estimator to speed up the evaluation of a design point and enable the design space exploration. And if we have a more efficient compilation flow in MLIR to generate RTL code, maybe in one day we can just directly generate the RTL code and do not need the estimation. We can just generate the RTL code and evaluate the RTL code for getting the latency and resource utilization, right? So both of this. Obviously it requires a huge amount of development efforts, but they are very exciting. Yeah.
Okay. Yeah, very nice. And then another quick question: is the code for this available open source or still the
Actually, we are working on.
ScaleHLS?
Yeah, we are working on an archive paper, and I think it will be released. I would say in this month, and together with the archive paper, we will release the source code and all of the benchmarks here and the optimization passes, the representation dialect will be available. Yeah.
Yeah, in one of the plots you were comparing with the slide 70, that one. So you were comparing with the TVM, and it's like a 4 times the speed up. So do you know what is the reason? Because the TVM will combine across stages. So it's because of the tiling, the poly transformation. Yeah. So what's the reason?
So here, actually, TVM, the main reason here is these models are not on the list of the officially supported model of TVM, of VTA, I would say. So if you look at the demo models provided by VTA, which is highly optimized, when you go through the TVM VTA flow, you can observe a nearly 2 DSP efficiency. So basically here, the maximum, theoretically, the maximum number of the DSP efficiency is 2. You can calculate 1 multiplication and 1 accumulation in 1 cycle for each DSP. So the maximum number is 2. And for the demo models of VTA, it can achieve something nearly 2 for like 1.7 or 1.9. But when I try to apply, these customized models to the VTA, it just said, oh, this layer configuration, like the kernel sizes, the feature map sizes, is we don't have a good answer or perfect answer for it. Then we will just use the regular or the most naive optimization flow to optimize these layers. So especially for I believe the first several layers and the classifier, so it is not optimized that good by the VTA flow. So the overall DSP efficiency is not that high. Yeah, but here I would say there's also limitations for the ScaleHLS flow, right? But these experiments are more to demonstrate that these complicated HLS designs are desired to be optimized at multiple abstraction level, right? And when we do it, it do achieve a significant speed up, and even achieve a very reasonable DSP efficiency. So that's the intention here, right?
Thanks for a really interesting talk. I had a question. So I thought it was really interesting the results you had that showed that the Pareto-optimal curve points were near each other in the PCA space. So that was a really interesting observation. Do you have any insights to why that might happen? I can imagine some points nearby in the Pareto curve might be nearby in the PCA space, but for the entire Pareto curve to be so close together is a little surprising. So do you have any insight?
So first, this actually not only in the PCA space, but also in the multi-dimensional design, but original design space, the variance of Pareto points are also smaller than overall variance. And actually, they are not like all the Pareto points are clustered together, but there are several small clusters, right? And that size Pareto point like to cluster with each other, and there are several clusters in the design space. So intuitively, if you think about it, for example, you find a very good loop transformation for this kernel, and then a pipeline initial interval of 2 or 3 or 4 or 5 or 6, have a high possibility that are also Pareto are dominating other points, because the loop transformation is good. And when you tune the initial interval of the pipeline, you are just a trade-off between the throughput and the resource utilization. And they are all Pareto points. And in the design space, they are clustered together. So so this is the like the intuitive understanding of this thing. Yeah.
Great, thank you. I think we have a student question I'll go ahead and read out. What about the accuracy of automation? Like in case of some complex systems, can the expected logical working of the baseline C code differ from what is emitted by the C++ compiler?
Sorry, what's the question?
So I think it's mostly, if I can read it, is about the correctness of the flow. So that you are going to be doing transformations, you are doing many things, and suddenly you can start to generate some C is your output, and then you pass to Vivado, but that it's not correct, or it's not equivalent to the input that you have. So what have you done on the correctness side?
Oh, actually,
how do you check the correctness?
Yeah.
Because if you do Verilog, you can do logic equivalent check, but if you do C, you cannot do much. So how do you check correctness here?
So can the expected logical working of the baseline C code differ from what? Oh, actually, it's a problem of comparing the functionality of the baseline C code and the emitted C++ code, right? So yes, I think you can. So I think the easiest way is to use the traditional, method. You write test benches to call the baseline C code and optimize the C++ code, and then you can somehow verify that they have the same functionality. But meanwhile, I would say this is a compilation flow, right? There must be some errors, and the verification of such a compilation flow is always a problem, right? And that's the reason why we have things like fuzzing and other verification techniques to verify that the input and output is the same, right? And I believe actually the verification of this of the ScaleHLS flow is also an interesting topic. Yeah.
Any other question from the audience? So there is a question on the chat. Maybe you can read it if you want, or we can read it to you, whatever you prefer. About MLIR.
I cannot read. I only see one question. It's the accuracy of the automation. Is there another question?
There's one on the chat, not in the QA.
Oh, let me take a look. MLIR could represent many levels of structure for each of those. Oh, I see. So I would say, yeah, this is true. So people with such a powerful infrastructure, MLIR, right? People want to design their own dialect to solve their own problems, right? And then you will have many different, loop level dialect in MLIR, which can do different things or can do well on different things, right? And I think for now, we are basically focusing on using the official or built-in dialect, which is a FUN and SCF in MLIR to represent the loop level IR. And it works well because MLIR already provide a large set of optimization, transformation, and analysis library to help us to facilitate all of the optimizations that are happening in ScaleHLS. So that's the reason why we chose to use a FUN and SF. But I would say if let's say we have another use case and we want to modify ScaleHLS to support a specific application, and for this specific application, I want to develop my own loop level dialect to represent it. Then just to do it, right? you write your own dialect and lower the graph level IR to your own dialect, and then connect the loop level dialect to the either a fan or the CPAP emitter to emit it, or if you prefer to lower it to LVM, then you lower to LVM and pass to the LVM compatible dialect. So I would say this is a common problem of MR, right? Whether you need to define a new dialect and what you want to do with the new dialect. And but I would say MR just provide you the flexibility to connect all of these components, all of the different dialects in the umbrella of the MR framework. Yeah.
Any other question? So just curious, so you have an approximate model for the delay and the performance, and you were thinking you were looking at AI for the future. So if you have to describe from a very high level, I'm assuming that you have to estimate what's the pipeline depth and the frequency that you can get. How do you do that? Do you have like you do consider just the number of gates on the critical path, or do you consider what are the main characteristics of that model? How do you get the time estimation?
So basically, from a high level, we are doing scheduling by analyzing the IR. So you have an IR there, and you can analyze all the dependencies, including the SSA, depth use chain and the memory dependencies. And on top of this analysis, you can do a scheduling. For now, we are doing AR/AP scheduling on top of the IR. And after the scheduling, basically you will have you will be able to estimate the latency of a piece of IR, right? And meanwhile, you can estimate the with the estimation of the scheduling, you can have the resource utilization scheme of the IR as well. So this will give you the latency and resource estimation. But a very critical question is how do you handle pipelining, right? So for now, we are also estimating the initial interval, the minimum initial interval that you can achieve based on two things. The first thing is the resource constrained initial interval. Basically, because you only have limited memory ports for the on-chip memories, so that will constrain the II you can achieve. And meanwhile, you will have those loop carry dependencies, right? If that is not resolved, or the distance between these dependencies are very close to each other, this means you can also achieve a very low initial interval. So we are using these two things to estimate the minimum initial interval you can achieve. And I think the estimation for the pipelining is the most difficult part of the estimation. And so let me think about it, whether there's other things. I think that's it. Yeah, and for now, actually, such a not that complicated approach is already very accurate. I would say, although in the downstream high-level synthesis tools, they are using more, advanced algorithms to do the scheduling, but in most cases, our estimation and the result reported by the downstream HLS tools is very close to each other, which is already enough to guide the design space exploration and generate a reasonable solution. Yeah, I think that's it.
Okay. Is any other question? No. Otherwise, let's thank the speaker. Good job. Very interesting tool. Physical clapping.
Thanks.
And good luck with your research.
Thanks, and thanks for the invitation. It's my pleasure to, give the talk here. Yeah.
Thank you. Bye.
Thank you.
Thanks. Bye.
Bye.